In this video, we're going to talk about the binomial distribution. All right, but before we do, we're going to start with a definition that we need, and that is a Bernoulli trial is a trial that has exactly two outcomes. For example, so it has exactly two outcomes. We decide which one's a success and which one's a failure. So one of them is a success and the other is failure. All right, it's pretty standard to denote the probability of success in a Bernoulli trial as little p, which means the probability of failure is 1 minus p, because there's only two outcomes, so p and 1 minus p. Some books denote the 1 minus p as q. All right, so some examples. Most common one is that you flip a fair coin. Now, you have to decide what's going to be success. So we'll say heads is a success. There's only two outcomes, which means tails is a failure. All right, that's a classic example of a Bernoulli trial. The probability of success then, since it's a fair coin, is 1/2, which is the same as the probability of failure in this particular case. 1/2, 1/2. Okay, another example would be rolling a 6-sided die. Now that might not sound like there's two outcomes, but let me first define a success. So let's let rolling a 2 be a success. Okay, so a 2 is success, and anything else, that is 1, 3, 4, 5, or 6, constitutes a failure. All right, so there's two outcomes, a 2 or not a 2. All right, and as we can tell by our rules of probability, the probability of success is 1/6, and the probability of failure in this case is 5/6. Okay, simple enough. All right, we're ready to define, actually I'm going to just come over here, a binomial experiment. Okay, so a binomial experiment, still haven't quite ready to define distribution, consists of a fixed number of identical independent Bernoulli trials. All right, I'm going to come down and break this apart into different conditions. So that's really what it is. It's a fixed number of identical independent Bernoulli trials. So whenever you're looking at an experiment and trying to decide if it's a binomial experiment, you kind of want to run through this checklist, especially if you're trying to decide it's one of many discrete distributions. So the first thing you want to see is, are there a fixed number of trials, which we denote pretty standardly as n. 2, each trial is Bernoulli. That is, there are only two outcomes, success or failure. All right? And the last one is that each trial is identical, that is, they're the same by Bernoulli, and they're independent of each other. So that is if I'm performing 10 Bernoulli trials, what happens on the first one has no bearing on the next, which has no bearing on the next, and so on. All right, so those three things need to be verified before you conclude that it's a binomial experiment. So an example, let's say we flip a fair coin 3 times. Okay, so let's go through our checklist. Fixed number of trials? Yes. N is equal to 3. I'm performing the same trial 3 times. Is each trial Bernoulli? That is, are there just 2 outcomes? Well, in this case, I flip a heads or a tails. I haven't yet determined which one's success or failure, but there are 2 outcomes. And is each trial independent of the others? Yes. If I flip a heads, it doesn't have any effect on the others. Okay, so that is an example of a binomial experiment. All right, now we're ready to define the random variable that's associated with a binomial experiment. All right, so in a given binomial experiment, to remember what that is, that should come to mind, those 3 things, we are going to let x count the number of successes in n trials. So if you're performing the trial 5 times, then x is going to be the number of successes in those 5 times. So what values can x take on? Well, you could get no successes. You could get exactly 1 or 2, all the way up to n. So if you have n right here, that means every trial was a success. And if you have 0, that means no trial was a success. Okay, so if we go back to our example, so remember the experiment of flipping 3 coins. Tails, tails, tails would correspond to x equals 0. If, remember what we decided, heads equaled success. All right, x equals, well, if I had something like tails, heads, tails, that corresponds to x equals 1. But by the way, so does heads, tails, 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 heads, and so on. So if there's exactly 1 heads in that group of 3, then that corresponds to x equals 1. Heads, heads, heads would correspond to x equals 3. Okay? Now, coming back to our discrete random variable here, I'm sorry, I didn't say that. We see that x is a discrete random variable. So that means any of our calculations should be sums and not integrals. Okay, when we have a random variable, so x is a discrete random variable, we want to be able to find the probability mass function, or the PMF. We want to be able to find the expectation of that random variable. We want to be able to find the variance of that random variable. All right? Onward. So we're going to develop those things with an experiment. Okay, I'm going to go back to this picture. So let's say we have 5 cards, these 5 cards. We shuffle them up and we randomly pick one. Let's let success be picking a king. that would mean failure is not a king. So a king or not a king, right? So two outcomes. I get a king or I get a not a king. So the probability of success here is 1 out of 5, whereas the probability of failure is 4 out of 5, because there's 4 ways I could not get a king. All right? Further, let's say we're going to perform this trial 10 times. That is, we're going to pick a card, record it, put it back in the deck, shuffle, and we're going to do it again. All right, so let's go through our checklist. Fixed number of trials? Yes. N equals 10. 2 outcomes? For yes, king, or not king. Are independent and identical? Yes, because I'm returning the card to the deck, shuffling, and doing it again. Okay, so the probability of success is the same on every trial. All right, so this represents a binomial experiment. And we're going to let x be the random variable that counts the number of successes. Okay, so x, in this case, could take on the values 0, 1, 2, all the way up to 10. Right, where 0 is where I get no kings on all 10 trials, and 10 is where I get a king on every single trial of the 10. All right, let's now see if we can construct the PMF. Okay, so let's start with, well, let's come back here and rewrite this here. So 0, 1, 2, up to 10. So let's consider the probability x equals 0. So remember what that means. That means no king. Which means if I were to write out my sequence here, 3, 4, 5, 6, 7, 8, 9, 10, all of those should be not a king. And since they're independent, I get to multiply probabilities. So this is 4/5 times 4/5 times 4/5 times 4/5, and I do that 10 times, right? Or 4/5 to the 10th. Okay, because I have failures everywhere along there. Okay, if I now want to look at the probability x equals 1, well, going back to my 10 slots up here, what I'm really saying is all of them are failures except one slot, which is a success. Let's say it's this particular one. Well, then what I see is I have failure, 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 failure. So these still are independent, so it's 4/5 times 4/5 times 4/5 times 4/5 times 4/5. And then I have my success, and then I pick back up with my 4/5 all the way down to a total of 10, right? That's that particular example. And so that, what do I actually have? Well, I have 9 4/5 and exactly 1 1/5, okay? And even if I move that S up front, I still am going to have 9 4/5 and exactly 1 1/5. The question is, so these are all different, so I have to sum them all up, is how many of them are there? So how many exactly 1 king scenarios are there? Well, that's equivalent to saying how many ways can I move the sequence of S, of 1 S and 9 Fs? Or another way to say that is, of the 10 slots, choose the one slot where I place the success. So there are 10 choose one ways I can have exactly 1 S and the rest failure. Then times the respective probabilities of each, 1/5, there's exactly 1, and then 4/5 to the rest, which should be 9. Okay, so that is, in fact, the probability x equals 1. Let's see if we can reason through the probability x equals 2. Well, we do know that there now in our 10 slots and so on, we know there are exactly 2 places where there are successes. How many? Well, of the 10 slots, choose the 2 places where the successes go. Then we see that we're going to have a 1/5 up there exactly twice, which means we have a 4/5 the rest of the time, which is 8. Okay, let's see if we can generalize it. What if I say the probability x equals k? That is exactly k successes. Well, that means of the 10 slots, I'm going to choose where the k's go. How many? I have k successes, so of the 10, choose where those k's go, which means I have 1/5 k times in there, and I have 4/5 the rest of the time. Okay? So let's go a step further and generalize. Let's say x is a binomial random variable, which means there's a fixed number of trials and the probability of success is p. Okay? If I want to find in general the probability x equals, we'll say little x, then that's the number of successes in n trials. So of those n trials, choose which ones of them are successes. Then I have the probability of success x times in there, and the probability of failure the rest of the time. Okay? And in fact, this is, sorry, I'm struggling with my pen. This is the probability mass function for the binomial random variable. All right? So this is your PMF. Okay. Depending on what level and what tools you get to use, you can construct, and the proof of that will be in a different variable, the expected value of a binomial random variable. So often the notation we use is x is binomial NP. So the expected value, which is the same thing as the mean, is equal to n times p. The variance of that random variable, which we denote sigma squared, is equal to n times p times 1 minus p. Well, that means if I need this, the standard deviation of that random variable, it's just the square root of the variance, right? Which is just sigma, which is the square root of n times p times 1 minus p. In another video, we'll have a bunch of examples.